Oh, hi there, and welcome back to exponential and logarithmic equations. Today, our final bit is with the natural logarithm. The natural logarithm it's just like any other log, really. It's just got a really special base. So in the world of math, there's this number called e. E is a number. Who knew? And it's not 5, just because E is the fifth letter of the alphabet. This is called Euler's number. Euler is not spelt like an Edmonton hockey team, but actually like this. Do not confuse that EU for the same EU you see in like Euclid. Euclid and Euler have very different ways of pronouncing this EU. Anyways, the number is defined as this. Some of you may have seen limits before, some of you perhaps not. But this particular little bit, 1 plus 1 over n, all to the power of n, changes as you increase the value of n. But it starts to hone in on something. So if we let n equal 2, we've got 1 plus a half to the power of 2, which is 2.25. If you let n equal 3, you've got 1 plus a third to the power of 3, which is 2.37037. And if you keep going with it, and let n equal 4, you're going to get 2.4414, stuff. It keeps increasing, but it increases at a decreasing rate. And eventually, some of these digits converge and they finalize upon a certain value. As you approach infinity, this expression becomes e, which to 3 decimal places is about this, 2.718. It's not exactly 2.718 because this number is actually irrational, so it doesn't terminate and it doesn't repeat. It just goes on forever, ever. But it has a place in statistics, compound interest, general calculus, and it's used for continuous growth. When a logarithm has base e, this is called a natural logarithm, and we use ln. So your calculator has an ln button, which is probably close to the log button, and we just use it to denote that special case of using e. So log base e of x is the same thing as ln of x, or ln x, as some say. Some say ln x, but not me. Your calculator will also have an e to the x button on it somewhere. So if ever you need to get the value of e, you're going to use that particular button. And it'll probably pop up with something like this. And you just have to say e to the power of what? If you want to see what e itself is, then say e to the power of 1. Just simple as that. So we're going to use this. We're going to use this in an example. And just getting familiar with using that button more than anything else. Worth noting is just as log of 10 is 1, or log base 2 of 2 is 1, you can also say that ln of e is equal to 1. And that's going to come into play with this example. So with continuous growth, we have the continuous growth formula, which is a equals PERT, as some call it, but a equals PE to the RT. P is the principal value, your initial value. What did you start with? R is your growth or interest rate. T is time. And R and T do have to use the same units for time. So if R is saying, oh, it's something per hour, but T is actually measured in years, you're going to have a discrepancy and it's going to cause issues. So that is something you have to account for. Hey, poops. Dr. Noel. Ooh, he sounds smart. He's probably like a chemistry and biology teacher, but also a doctor in this example somehow. He's discovered a new species of bacteria. Wow. takes a sample population of 100, places it in an area for optimal growth, and 8 hours later, its population is 720. So information I'm extracting from that is that's P, this is T, and this is A. So what's the approximate growth rate of the bacteria? Of everything in here, we're only missing one variable. Just noting that, don't forget, E is not a variable, it's a number. So from this formula, we plug in what we know. 720 is equal to the principal amount, which was 100. E to the R we don't know yet. And T it was 8 hours. And we're going to solve. I'm going to divide both sides by 100. And to get out of that exponent, I don't want to see any more exponents. I need to take the log of both sides. But I'm not just going to say log, because I know I'm dealing with base E. I know my calculator can handle base E as well. So I'm going to specifically use the natural log of both sides. So I'm going to take ln of 7.2 and say it's equal to ln of e to the 8r. This particular step, this line right here, is not necessary to show as long as you show the line here. So that's what you have to show. And if you want, you can write in that, like, this ln e, right? By the power law, this goes there. But ln e is equal to 1. So you don't actually need to write it. You can, and maybe I'll keep it there just for a moment and say this. But we're still not done. We just got to finish this thing off and say that r is equal to ln of 7.2 over 8, which is about 0.247 units, or bacteria, per hour. No, it's units. So that's the growth rate that we're dealing with. Now we're going to find out how much time it'll take for the population to be 4,000. When we do that, we're going to be using this rate, but we're not going to be punching in 0.247. We're going to be keeping things as exact as possible. If your calculator has a storage button, which might say stow, then you can take your value, like when you say ln of 7.2 over 8, once you have that on screen, press your storage button and store it in some variable, like a or x or whatever variables you have as options, so that you can recall it later using either it might have a mem button, or it might have an RCL for recall. It's more likely that it has this one. And if you need help figuring out your calculator, let me know, because this kind of thing can make your work much more efficient. So, how much time will it take for the population to be 4,000? We'll start with that same formula, A equals PE to the RT. And we're going to plug some things in. 4,000 is what we want the population to be. We started with 100. And e to the RT. I'm just going to keep it as r for now, so I don't have to write in the whole expression for it, which is a little complex. But isolating t now, we can divide by 100. And exponents, get rid of them. I will use the natural log. So the natural log of 40 is the natural log of this, which is what allows me to drop that exponent in front. And then I just have ln e. But that's just equal to 1, so I don't really need it there at all, do I? Then we're just solving for t. T is equal to ln 40 over r. If you want, at this point, you can sub this thing for r back in. over ln 7.2 over 8. And just playing around with that complex fraction. We can do that. You don't necessarily have to do these. If you stored r in your calculator, then it might be easier to just punch this one in. So ln 40 divided by, and then press your recall button to recall that variable where you stored the value of r. But if you didn't, then you're going to have to do these other steps. And even you don't even need this one. As long as you're comfortable evaluating from here, just don't forget brackets, they necessary. In any case, you get a value. I get 14.949. So the population will reach, 4,000 after 14.949 hours. This is actually a pretty common problem type when it comes to the natural log. So you might see some of them, like if you practice with past provincials and such. Practice will be coming soon for this one, but with this being the end of the topic, it's worth looking at the textbook review, but questions from the January 2019 provincial. I don't know if there's any long ones on there, but don't forget that there does also exist the database of past provincial questions, and many of those will have ln, or the natural log, involved as well. As always, let me know if you have questions. Let me know if you have questions on this lesson. Let me know if you have questions on any of the practice work. Do the provincial questions, do these ones, do the ones that are online. Check out their marking guides, don't forget that. And always let me know if you have questions so I can help you out as best I can. That's it for now. Topic 6 has been a slice, and I'll see you at topic 7. Goodbye.